Hey guys, so today we're going to continue talking about changes of state, specifically the energy involved and kind of where that energy goes and what happens to that. So the first thing we're talking about is going to be equilibrium. And when things get out of equilibrium, is when you notice changes happening. So if you're thinking about liquid, this example, I use a bottle of isopropyl alcohol because alcohol evaporates very easily. Same thing can happen with any bottle of liquid you have that has a cap on it. So if you have like a bottle of water, a bottle of soda, whatever, if you get enough energy to cause those molecules to evaporate, you're inside of a closed system. Okay. So in a closed system, you will reach equilibrium because you have these changes occurring in opposite directions at the same rate. Okay, so eventually this liquid starts to evaporate. Now you have this little space up here where the air is, where you have vapor being formed from the evaporation, which causes vapor pressure up against the sides of the container. Okay, so now we have vapor pressure. Once that gets high enough, it's going to cause condensation. So once that system starts changing, you're going to have an equal rate of evaporation compared to condensation. So that's when you're going to get an equilibrium. Okay, so some other processes that can also cause equilibrium in a system or just really motion of particles once we're talking about that is we have effusion and diffusion. So effusion is going to be when a gas particle is going through a tiny opening. Okay, so this is going to be some kind of system that is partially closed and the gas particles kind of move through this small area. Diffusion is just going to be spontaneous mixing. Okay, so diffusion is what you get when you light a candle and now you can smell it all over your room. Okay, you have these little particles and they're just kind of moving about freely. So the rates of effusion, not diffusion, effusion, are going to be directly proportional to the velocity of their particles. Okay, the mass is also proportional. Okay, so when we're talking about this system, and let me go back here. Let's see. Okay, here, so we're talking about effusion, where we have this like little space where these particles are moving through. It would make sense, right? The rate by which they will move through that space is dependent upon its mass and its velocity. Okay, so molecules of low mass, things that are lightweight, they're smaller, they're going to move faster. Same thing with molecules that are already moving faster, they're going to move past that barrier more quickly. So that relates back to the heat that's present in that system, right? So we know already that the average kinetic energy of molecules of any gas is going to be dependent on the temperature. So if you're adjusting the temperature, you're going to be also directly a direct relationship adjusting the rate of effusion. So this little formula on the right-hand side here, this is 1/2 mass times volume squared is equal to 1/2 mass times, velocity squared. This is actually also used in physics. So whenever we have these, we're talking about the motion of the particles. So we're talking about like 1 mole of something, or one molecule of something moving back and forth. So if we adjust the mass and the velocity on the left hand side, that's going to affect the right hand side. Okay, so we're talking about the motion on the first side of the container versus the motion on the second side of the container, right? So if we increase these, they will move faster over to the other side. So with Graham's law of fusion, he's going to be talking about how the effusion rates of gases at the same temperature and pressure are inversely proportional to the square root of their molar mass. And that was just like a lot of words there. So I just wanted to show you this relationship. For now, we're not going to get into this as far as figuring it out mathematically. But when you're trying to figure out what the rate of effusion is for these gases, it's important to know their molar masses and the temperatures involved. And so you can look at this chart here, and it gives you a nice description of what's going on. So we know that helium is going to be a very, very lightweight molecule, and it's going to have a really high rate of diffusion or effusion. Okay, and so as you make your way down to these heavier molecules or larger molecules, you're going to have a slower rate of effusion, okay, because they're just going to move around slower. It's kind of like I always think of like my dogs, right? So I have two dogs. One of them is slim and trim. She runs around pretty fast. The other one's short and fat, and he does not go as fast. So it's kind of the same idea there. So if you have a bigger molecule, it moves slower. That also has to do with the volatility of liquids. Okay, so volatile liquid just means that it is going to easily evaporate. Okay, it means that it is requires a very low amount of energy to cause that evaporation to happen. So you could increase the pressure a little bit, or you could increase the temperature a little bit, and it's just going to evaporate. So you could think of like rubbing alcohol. It's pretty volatile. It's going to evaporate pretty easily just at room temperature. So there's some other examples here, like butane. This is like a fuel, a gas that you can burn. So that's going to be pretty volatile. I mean, all of these ether, like that's very volatile. So as you get through here, it doesn't require any of these would require very much pressure or temperature increase to force them to evaporate. So any volatile liquid, it's going to be easier to identify because they have low boiling points, okay, because they require little energy to change. High vapor pressures, okay, so at rest, they're going to have high vapor pressures. They're going to have strong odors because they're easily moving. Those molecules are jumping out of the substance and diffusing, so that's what you can smell. And obviously, they're going to evaporate very quickly. What the kind of key part of this lesson is the molar enthalpy of vaporization. Okay, so or just molar enthalpy in general. So the molar enthalpy is talking about the amount of energy it takes to cause that phase change to happen. So in this slide in particular, it's referring to vaporization. It can refer to freezing or melting, any of the phase changes. It's how much energy does it require to make that happen. So we're going to have this formula that we're going to use. Q is the heat energy. Okay, it's measured in kilojoules. That part's not as important. I just want you to recognize that it's in kilojoules because the molar enthalpy of fusion or vaporization is also in kilojoules per mole, and you always have to have your units matching. Okay, so energy is going to be in kilojoules. That's going to be set equal to the amount of the substance you have, so in moles, and then times the molar enthalpy of fusion or vaporization. So the delta H is going to be a constant, so that will be given to you, or you could solve for it if you knew the other two things, but most of the time, this is already known and given. So you will have to be figuring out how many moles of a substance you have and then calculating the amount of energy it takes to make that change happen. So the molar enthalpy of vaporization is going to be how much energy is needed to cause 1 mole of liquid to evaporate. Okay, and then the molar enthalpy of fusion is going to be how much energy it takes to melt 1 mole of solid. So if they have a stronger attraction, it means that you have more energy needed, which leads to a high molar enthalpy of vaporization. Okay, so when you have high molar enthalpies, you're going to require more energy to break those bonds. So the example here is of an orange tree, right? So normally, oranges were grown in tropical environments. Down in Florida is a big grower, producer of oranges, California. So whenever it gets cold in those areas, it will kill the trees. So instead of just letting their trees die and losing their entire crops for the year, we just recently had like a cold snap down in Florida, the farmers come in and spray their plants with water. And that seems counterintuitive, right? So they're spraying their plants with water, just coating them in water right as it's about to freeze outside. What that does, though, is it actually protects the plant because you're spraying them with water, and as the water freezes, the heat that's required to freeze, that you need to remove a certain amount of heat to freeze the water, that heat is transferred into the plant. Okay, so it creates this little like thermal pocket for these plants and for the fruits on them, so they don't actually get down to freezing. Now, this obviously only works for like a brief cold snap. This wouldn't work here because it's just too cold here all the time in the winter for that kind of thing. But it does work in other climates where, like in Florida, where it might get down to 27 one night and then it's back up to 50 the next day. So by spraying these with water, the heat lost from the water in the process of freezing the water goes into the fruit and keeps it warm. Okay, so this I want you to think about. Okay, we've all seen this. If you've ever baked anything at all, you've noticed that on the back, like with the directions, it always has a high altitude instructions included. I want you to think about why, and kind of when we're talking about the energy of things involved in causing these changes to happen, and pressure. Okay, so when we talk about high altitudes, we are up very high, the pressure is lower. Okay, so we're going to end up here with boiling points that are different at different areas because of the the the, the Okay, so when we're up in these higher altitudes, they have lower pressures, right? So you're way up high, you're further away from the center of the earth, right? So you have a lower pressure up there because there's less gravity pulling down on molecules and keeping them close and condensed. So if we just take like Denver, Colorado, for instance, that's somewhere pretty easily accessible. I'm sure some of you have been there. The elevation is going to be 5,000 feet above sea level. Sea level is down here. In Missouri, we're like slightly above that. I'm not sure where we're at exactly, but we're somewhere in here. Denver's much higher than Missouri. So when we bake things here, we don't have to adjust for anything because the directions are made for most conditions, right? And most conditions are not going to be very high altitudes. But in Denver or any of these other higher altitude places, you have to account for that because when you have a lower pressure, you're going to have a different boiling point. You're going to have a lower boiling point because by definition over here, a boiling point is the temperature when the vapor pressure of your liquid is equal to the atmospheric pressure, okay? So when the pressure is lower, the boiling point is lower. And if the pressure is higher, the boiling point is higher. Okay, so if you were below sea level somewhere and trying to boil water, you would have to get the temperature even higher to cause it to boil. So because of that, you get these like wonky looking baked goods that just overbaked probably, and most of the time you'll notice that the temperatures are going to be set at a lower amount and they have to adjust for the amounts of ingredients for that. So freezing point, also in the same kind of context here, freezing point is the temperature when the solid and liquid are in equilibrium at 1 atmosphere of pressure. Okay, so when your solid and liquid are in equilibrium at 1 atmosphere of pressure means that they're going to kind of slow down enough that those bonds will form between them. Phases, one more time, I just wanted to hit this because after we kind of talked about it in class, I realized that some of you guys either didn't learn some of these phase changes or just don't remember them. So if we're looking at this diagram on the left here, we know that we have solids, liquids, gases, and plasma. You guys are very aware of that. The enthalpy of that system gets higher the more energy that's required, right? So solids have a low enthalpy, like the amount of energy in them. Liquids have more, gases have more, and plasma has even more. You do need to be familiar with these phase changes. So all these little arrows in between. So we know that the difference between solid and liquid is freezing and melting. Gas to liquid is going to be condensation. Liquid to gas is vaporization. Okay, those two you need to know. So you're creating a vapor or you're condensating something. Gas to solid and solid to gas. These are the ones that everybody was missing whenever we were talking about it in class. So gas straight to solid is called deposition. Okay, so it does not turn into a liquid first, it just condenses, it goes straight from a gas into a solid. That's deposition. Sublimation is the opposite. So, sublimation would be a solid straight into a gas. So, think like a chunk of dry ice. Okay, it's not melting into a liquid, it's just turning into a gas. Up at the top part here, a gas into a plasma is ionization. Okay, so you are adding so much energy to the gas that it's causing those electrons to remove themselves and create all these little ions. And then the other way from a plasma back to a gas would be recombination. So, kind of brush up on those terms if you are not familiar with them. On the other side here, we have the triple point and the critical point, which we did already talk about a little bit. So your triple point is going to be when a substance can exist as a water, a liquid, and a gas. Most of the time, you're going to have to remove the pressure and lower the temperature. So you're going to have to lower your pressure pretty significantly, and then also lower your temperature some, and you can get like a chunk of ice in boiling water. The critical point is up on the top right-hand side. So this is going to show your temperature and pressure when a substance just can't exist as a liquid anymore. So obviously that can be at higher temperatures or higher pressures. So once they get beyond that, they'll just turn into a gas, and then if you add even more energy, you get plasma. So this is your triple point of water. I wanted to show you guys this. This you'll need for your lab, so just come back to that later. But I wanted to show you here what this actually looks like. I can't remember if there's actually sound on it, but this is inside of a vacuum. Okay, so imagine like a big like glass bell around it, and it's inside of a vacuum. They've lowered the pressure. Okay, so they have sucked out, they've used the vacuum. When they lower the pressure, this starts out as ice cold water. They lower the pressure enough, you get ice that forms on the top. You can see this small layer of ice on top, and then it's boiling underneath. That is your triple point. Okay, so you're creating a gas. There's obviously a liquid in there, and then the solid is on top. So that is it for today's notes. This heating curve of water you will need to reference for your lab. So when you get in there, this lab is the same lab we're doing in class. You are given the data though. If you have a thermometer at home and you're allowed to boil water, you're more than welcome to try this at home. It's kind of cool actually to see it actually happening in real life. It's a relationship that you don't notice unless you're paying attention. So if you want to do this at home, you're welcome to do that. As long as you just have a timer. You have a timer on your phone, and then you can boil water and watch the temperature as the phases change. So if you'd like to do that, you're welcome to do so. And please let me know if you do have any questions from today's lesson.